Hi, good morning everyone. So like I said, I'm not here this morning. I'm bringing my mini students to the field trip, and I will be back this afternoon if you need to find me. Okay, so I'm going to do I'm trying something new here. I've never done a screen recording before, so let's see how this works. If everything works well, maybe this is how I'm going to teach you in the future. All right, so remember last class we were working on drawing Lewis diagrams, okay, Lewis dot structures. And I'm just going to start with a quick review with you and going over an example. And remember, next class we will have a little quiz just on Lewis diagrams. So for block 2-4, since you guys are having a presentation in the auditorium, you will be coming to see me during eye time. Okay, so come at least maybe 15-20 minutes early, and around 8:40. Okay, come do a quiz and then pick up a couple sheets, and then I'll send you down to the auditorium. For block 3-4, we'll do it in class, and then we'll go over a couple examples and review. All right, so I'm going to begin with an example, doing a new example with you today, just as a quick review. So let's work on this one together. So N2, H2. So remember rule number 1, you want to arrange the atoms so the single one is in the middle. So now for this one, since both of them, they have 2 of them, so they are equal. But remember, for hydrogen only wants to have 1 shared pair, and which means they are always on the outside. So with that fact, you should be able to place nitrogen in the middle, and then for hydrogens, they're always on the surrounding. All right, so step number 2, count up all valence electrons. So we have 2 nitrogen atoms, and look at the valence electrons for nitrogen. Looking at your periodic table, going across, and you should see that they have 5 valence electrons. So 2 times 5, 10. And I have 2 hydrogen here, that means 2, right? Add them up, 12. So 12 divided by 2, that would give you 6 pairs of electrons. So you only have 6 pairs. That's all you're going to use. You're going to use them all to make all the atoms happy. So we're going to begin with single bond. 1 single bond between 2 atoms. Join them all together. That uses up 3 pairs. So that means I have only 3 pairs left. So check hydrogen. Hydrogen is already happy because it only wants 1 pair. So for 3 pairs, you know it's an odd number, it's hard to share. So you can still try if you want to put two pairs on 1 hydrogen. That makes this hydrogen happy. But you only have 1 pair left for this hydrogen. Okay, and now you use up all the pairs. This hydrogen here only have 3 pairs of electrons, which means it's not octet, it's not happy. So with that, you know that this is an incorrect Lewis diagram. Okay, so we're going to cross it off and do another one. So remember step number 6, the last step, it says if a single bond doesn't work, you need to change it to try a double bond. Okay, and we want to try a double bond between the 2 hydrogen, because between the 2 nitrogen, because you know the hydrogen doesn't want 2 pairs. Okay, so that used up 4 pairs, and we are down to 2 pairs, and they can share them equally, 1 lone pair for each of the 2 hydrogen. And now it's time to check for octet, right? So look at the central atoms, nitrogen, and they have 4 pairs. Okay, so make sure you always check for octets. 1 pair, 2, 3, and 4 for 1. And the same thing for the one on the right hand side. Okay, so that means this must be the correct diagram, Lewis diagram for N2H2. All right, so that's the review from last class. That's what we learned last class, and make sure that's what you're going to be studying for Friday. And just remember octet. Okay, 4 pairs. They always want to achieve to have 4 pairs of electrons. Okay, and for today we're going to be learning some exceptions. Okay, so this is not going to be on the quiz next class, and in fact there are only a small number of molecules that have exceptions, and I'm going to ask you to remember one of the incomplete one, and then the other ones are actually pretty easy to know. So there are 2 different exceptions to the octet rule. The first one is the incomplete octet, which means less than 4 pairs, right? And the second one is called the expanded octets, which means more than 4 pairs. Okay. Now, for the incomplete octet, there are actually the only atoms that I know that has an incomplete octet is boron. Okay. So boron is the one that I'm going to ask you to remember. Boron is going to be the central atom that has an incomplete octet. And we're going to take a look at this example here, BF3. So we're going to basically using the same method we learned last class. Okay, step number 1, place the central atom in the middle, the single one in the middle, and then the other one go around it. Step number 2, count up the valence electrons. So boron, looking across the periodic table. Okay, so 1, 2, and 3 valence electron, 3 electrons. And 3 fluorine, each one of them has 7. 3 times 7, 21. So in total, we have 24 valence electrons. And I'm going to divide that by 2, which gives you 12 pairs. So you're going to start with single bond. Place 1 share pair between 2 atoms, join them all together. That use up 3 pairs. We have 9 pairs left, and you divide it by the 3 fluorine. You're going to give each of the fluorine 3 lone pairs. And now you use up all the pairs of electrons, and if you remember what we learned last class, we had to check octet, right? So fluorine is happy, all the fluorine atoms are happy, but boron is having less than an octet. Okay, it only has 3 pairs of electrons. So I need you to remember boron in this case, that's what it will settle with. Okay, it only wants to have 3 pairs and it's going to be happy. And this is the only exception, okay, that you need to know. And in other cases, you will have to try double bond, but not for boron. Boron is happy with just having 3 pairs. And I will talk a little bit more why that's the case when I'm going to talk about combining capacity at the end. Okay, so we're going to come back, but that's the incomplete octet. That's the exception to the octet rule. All right, so moving on, expanded octet. So for these molecules, the central atoms is able to have more than 8 electrons, So that is an expanded octet, more than 4 pairs. And the reason to do with that is in the 3rd row of the periodic table, there are some D subshells available for bonding. So for example, if you look at some of the examples here, phosphorus and sulfur, when they are acting as a central atom, go to the periodic table, phosphor and sulfur, they are able to use the d orbitals, okay, for filling in extra electrons. So they have electrons in the 3p orbitals, but they can also access the orbitals in the 3d, which is not too far away from the 3p orbitals. Okay, so and that's the reason why they can have an expanded octet. So if you just simply look at these examples, PCl5, automatically you know that there must be 5 chlorine atoms joined to a phosphorus, right? So automatically you know that it's an expanded octet. So for cases like that, it's actually pretty easy. You know automatically just by looking at the formula that you know this is an expanded octet, is an exception to the octet rule. Okay, but other than that, we're just going to use the same method that we did for all the to draw the Lewis diagram. So phosphorus, it has 5 valence electrons, and we have 5 chlorine atoms. So 5 times 7 would be 35. So in total, we have 40. Okay, and 40 divided by 2 gives you 20 pairs of electrons. So you're going to use up all 20 pairs and to see if you can fulfill octet rule for chlorine, but you know for a fact that phosphorus is not having an octet. It's having an expanded octet. So 20 minus 5. Now I use up 5 share pairs, bonding all the atoms together, and I have 15 pairs left. 15 pairs divided by 5 chlorine atoms. That's equals to 3. They have 3 pairs each, which is perfect to make each chlorine atom happy. Okay. So now those are the 15 pairs of lone pairs plus the 5 share pair in the middle. I use up all 20 pairs, and that's the end of this molecule. It's all done. And I'm going to ask you guys to try the second example here. Maybe Ms. Yu can pause the video a little bit and let everyone to have a chance to try the second examples on their own, and then show the answers. So if you have done your calculations correctly, you should have got 24 pairs of electrons. So that's all you have. And sulfur in the middle, 6 fluorine atoms around sulfur. And we're going to use 6 share pairs to join all the atoms together to the central atom. And that would take away 6. 24 take away 6 would be 18. I have 18 pairs left, and I have 6 fluorine atoms. That means each atom must get 3 pairs, 3 lone pairs, which is exactly what they want. And that's it. That's all you have. And sometimes, if there are extra lone pairs left, you can actually just put the lone pair in the central atom, and that's also considered as correct for sulfur and phosphorus. And usually, it's these 2 nonmetals that are able to have extended octet when they are bonded to other atoms. Okay, so these are the 2 scenarios for exceptions. The incomplete octet and expanded octet, and they won't be on the quiz next class. So all the ones that you're going to do has to make sure you fulfill the octet rule. And there are not too many exceptions I'm going to give you. Alright, so make sure you focus on remembering the octet rule. Alright, so other than the exception, another thing that you need to know for drawing Lewis diagram is called the resonance structures. Okay, and for resonance structure, it's basically a case where there is no one structure that could adequately represent one molecule. So you actually have to draw more to represent one molecule. So the example I'm going to show you here is NO3 minus 1. And this one is actually one example that you did from last day's homework. And if you can just quickly look at the previous page, NO3, look at your answers for NO3 minus 1. And I'm going to ask you to copy it onto your notes. Okay? And if you have done everything correctly, nitrogen in the center, and you have 3 oxygens surrounding it. And if you do your calculation, there should be exactly 12 pairs of electrons. And to make everybody happy and to use up all 12 pairs, there has to be one double bond between one oxygen and the central atom. So that means there will be 2 lone pairs on this one on the left, and then 3 lone pairs for the other 2. And that would be exactly 12 pairs of electrons. And don't forget, bracket with a charge on the upper right corner. Alright, so now I'm going to ask you guys to think about this structure. Look at this structure and tell me if you could draw another structure that is pretty much the same thing, but it's a different one from this one. And how could you draw the second one? So take a moment to think about, for example, this double bond. Where else could you draw this double bond? So it's not, I'm sure you guys are able to tell, it's not, for this double bond, you could place this double bond here or here, okay? And they are pretty much the same structure. So therefore, these 3, you should be able to draw all 3 structures, and they pretty much represent the same molecule. And these 3 structures are called the resonance structures, okay? Because the double bond is not fixed with only one oxygen. In this case, is actually going around sharing among 3 other oxygen. So I'm going to show you a diagram here. Where did my diagrams go? I'm going to pause it for a sec. So here is the picture, the Lewis diagrams for the 3 resonance structures for nitrates. So as you can see, the double bond can be either in one of the 3 oxygen atoms. So they are just, keep rotating. They are not fixing, they're resonating around the 3 oxygen atoms. And another way that, we can draw this resonance structure is like this, okay? And because the fact that, the double bond is actually not fixed, they're actually going around. And that's what these dotted lines are representing, because the double bond is equally sharing among the 3 oxygen, between nitrogen and oxygen. Alright, so that's resonance structures. So if you have a question like this, make sure you draw all 3 to represent the answer for nitrate. Okay, so in cases where there's like usually a double bond and single bond, and where you can pretty much draw the double bond somewhere else, and that's where you will see those resonance structures. Alright, the last thing I need to talk about today is called the combining capacity. And sometimes you will encounter a situation where there are 2 structures that both of them fulfill the octet rule, but there's only one correct answer. And for those cases, you need to check the combining capacity of the atoms. So for combining capacity, it's basically another word for the number of bonds an atom likes to form. Okay, so the number of bonds an atom forms corresponding to its combining capacity. So it's like the preference of the atom, how many bonds they would like to form with another atom. So one way that you can easy way to remember the combining capacity, again, go back to your best friend, and it's to do with you know, the same song that I taught you. And remember 1 2 3 4, 1 2 3 4, 3 2 1. And actually these numbers is not just representing the charge, but also the combining capacity of the atoms. So for instance, boron, remember that's the exception that we talked about today, it actually prefers to have 3 bonds. Okay, carbon, they always like to have 4 bonds. They don't like to have like lone pairs or 3 bonds or anything less than 4. They only want 4 bonds. And for example, all the halogens here, they only like to have 1 single bond. They can never ever form a double bond with something else. Okay, now the only exception that could be a little bit changing are these ones. Okay, nitrogen, oxygen, phosphorus, sulfur, they could have, you know, 3, but 3 and 2 are their preference, but they could have more or less bonds. Okay, so going back to the example for today, it's CO2. So CO2, carbon dioxide, is an example that you did last class for homework, and I'm sure a lot of you got this answer, right? CO2 double bonded to 2 oxygen atoms, and from your calculation you should get 8 pairs. But I'm not sure if some of you might get a different answer. Okay, so instead of getting this answer, there could be a different answer that are also considered to be correct according to the octet rule. So I could have a triple bond and a single bond, 1 pair for 1 oxygen and then 3 pairs for the second one. And the same thing, I used up all 8 pairs, and it's all octet rule for all the atoms. So in situations like this, you will have to check the combining capacity of the element, what they really prefer to have in terms of bonding. And if you remember, carbon always want to have 4 bonds. Okay, 4 bonds here for carbon, and for oxygen atoms, preferably they want to have 2 bonds. Okay, so that's what this 2 comes in. They want to have 2 bonds, so that's why this one is the correct structure, Lewis structure for CO2. Okay, and just quickly recall what we did today on BF3. Again, to check the combining capacity, boron wants to have 3 bonds. Fluorine, you see, in this case, fluorine always want to only have 1 bond for combining capacity. Okay, so all these are combining capacity. So in this case, you actually don't want to create a double bond here because fluorine actually can't handle a double bond. And so that's all the best we can draw for BF3. Okay. And one last note, combining capacity, carbon, remember, carbon is actually always want to have 4. Doesn't matter single bond or double bond or triple bond, they always like to have 4 share pairs. So I'm just going to make a note here saying that carbon atoms like to, actually, you know what, I'm going to say carbon atoms do not like lone pairs. Alright, so that's the end of today's lesson. So Miss Yu is going to give you more instructions on what to do, and I shall see you guys on Friday. And don't forget about the quiz. What is helpful from today's lesson for the quiz is the combining capacity. So make sure you think about combining capacity when you build a model, and resonance structures may or may not be on the quiz, but no exceptions definitely. Okay, so the exceptions, incomplete or expanded octets, they won't be on the quiz. Alright, so I will see you guys on Friday. Have a nice day.